Welcome, welcome, welcome. So in this video, we'll be talking about sets. So what does a mathematician mean when they say set? It's just simply a collection of things. These things can be anything you like. Often there's some common property with these things. So it might seem kind of weird or pointless to just collect a bunch of things, but sets are really a fundamental property of mathematics. It gives us the starting point, the building block to our language that we might be using. And many mathematicians have built subject areas that start off with sets. So a few examples are graph theory or abstract algebra or real analysis, complex analysis, linear algebra or number theory. These are all university level courses in mathematics. For this course, we're more interested in different types of numbers. Like you might say, okay, we have integers like 1, 2, and 3, or you could also have negative integers, or even fractions like 3 over 5. And then we might be interested in, well, what's different from a number like that to a number like the square root of 2, where you have like a real number that you cannot represent as a fraction. We call those irrational numbers, where these ones are rationals. And we might be even looking a little bit further beyond just numbers. We might also look at objects, just to represent some of the ideas of the language that we're going to use. Now, most of the lectures will have a warm-up problem for this course, and this particular lecture is no different. Our warm-up problem is called the notation motivation. So many people often find mathematics daunting, and this intimidation often comes from the notation. Mathematical thinking itself, I would say, is both beautiful and playful, and should not be the cause for fear. That should be a fun, creative thing to do. But often mathematics is taught in possibly, in my opinion, the wrong order. Notation first, and it ends up looking like some alien hieroglyphics of no use. And then the mathematical thinking, the beautiful part, comes secondary. So let's try to switch this up. Let's say I'm not going to give you any notation to begin with. I just want you to come up with some ideas to represent the items below. And there's no wrong answer. So just pause the video and work on these 4 things. Okay, so if you've tried this on your own, now as an instructor, I have some motivation to give you the notation that mathematicians have generally agreed upon to represent things like this. So if we're going to make notation to represent the set of all classes we're going to take this year, mathematicians have arbitrarily decided that this is the symbol to contain a set, these curly brackets. So everything that's in the set goes inside of the curly brackets. And maybe the class that you're taking is Math 160, maybe there's some other ones, but this might be how a mathematician would notate that. The set containing nothing, you could just write brackets with nothing inside. That's one possibility. Another way that the mathematicians have decided to do this is write a 0 with a strike through to represent the set containing nothing, or called the empty set sometimes. So we could represent all stars in the universe by saying we're going to build a set and then say all stars, like that. The last one, we'll come back to it later, formally, how you could represent this. It's a bit of a goofy example. You could say S is a set, and then you could write a bar to put a condition that this set does not contain itself. So this is a bit of funny notation. We're going to learn about this notation soon. Okay, so why should we study sets? It's really the starting place to learn algebra and the starting place to learn the language of mathematics. So mathematics is not just about numbers. Often it's taught with just numbers, but there's much, much more to it. Here's some popular quotes that I've come across over my time to share that with you. So forget everything you know about numbers. In fact, forget everything you know about what a number is. This is where mathematics starts. Instead of math with numbers, we now think about math with things. I don't know who said it. Here's another one. Saying mathematics is only about numbers and equations is like saying English is only about letters and grammar. So maybe think about those ideas when you are teaching mathematics. And when mathematicians get some kind of idea, we write a definition to represent that idea. But the definition doesn't come out of thin air. It's not something that we just make up randomly. There's always some kind of motivation to building a definition. So when we learn new words in this course, they might be familiar words to you, as in they're used in the English language for other things, like we're going to define elements right away. And elements, of course, is a word that's used in the English language in many different contexts. But now when we say the word element for our course, we'll mean something very specific. And the same goes for other definitions. So an element can be anything imaginable, and it's something that goes into your set. So the elements build our set. So one way to formally build a set is just to list all of the elements. So this would be called set list notation. You can start making your set by opening up the curly bracket like we did in the warm-up problem and closing off the curly bracket when you're done your list, and everything in the middle is the list of stuff. Okay, so for example, you could list the 5 largest countries in the world: Russia, Canada, United States, China, Brazil. So it's not necessary to write your set in a particular order. This time I wrote it from largest landmass to smallest landmass out of those 5 countries. It's nice to write it in a logical order sometimes, but you don't necessarily have to do that. Okay, so sometimes sets are too big to list out each element individually. In this case, we need to describe what our set is in a little bit of a different way, trying to display some kind of pattern. And another definition for you, the ellipsis symbol, or 3 dots. 3 dots written just like that. What that means is that there's some pattern that continues on and on and on. And hopefully by the context of what's going on, that pattern will be clear. So even integers, this set would go on and on and on, meaning that 10 is also in the set. It's not listed, but it's there. And 12 is also there, and so on and so on and so on. All the positive even integers. And we could even say the set of prime numbers. So 2, 3, 5, all the way up to 17. The next one that would come along in this list would be 19. It's a prime number. It's not listed. All the prime numbers are there. We just write ... to represent that idea. Okay, now if we need to get even more fancy or complicated, we use builder notation. So the builder notation we briefly discussed in the warm-up problem, or very briefly. We build it again with curly brackets, open set, close set. Now this time what goes on the left-hand side of the bar is what the stuff in the set looks like. Some brief description of what you have. A number, a symbol. It could be many different things depending on what you're trying to do. And then any conditions that might come up go on the right side of the bar. So the bar itself means such that. So what the things look like, such that particular conditions are true. So for example, if we wanted to have the set of even integers, instead of listing it with the pattern, we could write out the following here. We can say that n is an integer such that that integer is even and it's positive. So both of those conditions are true. The set of prime numbers, we could say that n is an integer, that's what the things in the set look like, and 1 and n are the only factors of that particular number. So that's a condition. Also, 1 itself is not defined as a prime number, so we skip that one out as well. So a quick little note before moving on. Often, instead of writing out an English sentence like n is an integer or a phrase, we'll have symbols to describe that in the future as we get more and more specific as we go through things. Okay, so moving on. Sometimes we want to single out a single element within a set, and that's the motivation for this definition below. It's like you have a barrel and you want to dig your hand in the barrel and pull out a particular marble or something like that. That's what this does. So this kind of funny symbol, it's like a C with a line through it, is read as is an element of. So for example, fox is an element of the set of all animals. So fox is an element of the set of all animals. So you can also negate any mathematical relation. So this symbol here is a relation because it relates an element to a set. It relates what's on the left to what's on the right. And you can negate things by putting a little strike through, meaning that fox is not an element of birds. So a set with no elements is known as the empty set. Some people even call it the null set, and it's notated by this little 0 with a line through it. So countries that are south of the South Pole would be nothing. Okay, and we're also going to work with sets that have numbers. We're not going to ignore the numbers altogether. It just all fits together with numbers and things that we might want to work with. So here we define some commonly used symbols for the real numbers and different categories of numbers within the real numbers. So the natural numbers are notated with this boldface n. The natural ones are the ones that we naturally count, 1, 2, 3. And the integers will also include 0, -1, -2, and all the negative natural numbers as well. The real numbers are any value that's represented along a continuous line, or any digit with a decimal following other digits are real numbers. And they don't have to have a decimal place. All of these ones listed above are real numbers as well. Now, two categories of real numbers are the ones that can be represented as fractions and the ones that cannot be represented as fractions. And here's our rational numbers in set builder notation. So again, what do things in the set look like? They look like something, bar, something else below the bar, such that n and d are integers, so they're members of this set, and d itself is not 0. So those are our conditions to put things into this set. The most common symbol used for the rational numbers is Q, the boldface Q. And if you want to collect numbers that are not rational, then you can say R minus Q. So we're taking away all of the fractions and we're just left with numbers that are no longer fractions. Okay, so it's always nice to picture things, where these numbers land. So in this picture, we have real numbers, and we're supposed to write some examples in each section. So how about for the natural numbers? One natural number that we can think of is 1, or you could write 2, and something else that you could write. Maybe Connor McDavid is in there too. All of those numbers are examples. We won't write all of them, just some examples. And then maybe an example of a integer that is not a natural number. Maybe we'll put minus Wayne Gretzky because he no longer plays. Okay, now how about a fraction that's not an integer? So something outside of that box we were just inside. So maybe we'll write 1 over 2. Or maybe you compare Sidney Crosby to Connor McDavid. All right, so some examples of numbers that we cannot represent as fractions or irrational numbers would be numbers like square root of 2 or pi or the constant e. It turns out that these numbers are all not equal to something of the form a over b. So there's no a and b that you can pick to represent those as fractions. Okay, let's do some more practice. So I suggest to pause now and see if you can figure out some of this on your own before I give you the answer. Okay, so if we're going to convert 5 is an element of the integers, what we would write down is the symbol 5 for the number 5, and is an element of, remember that looks like that, and the integers is a boldface Z, like that. Okay, so if we want to convert the following into builder notation, we have the integers 5 to 9, or natural numbers, because there's no negatives in this list. So we can say that n is an element of the natural numbers such that this number n is in between 5 and 9, and including 5 and 9. So I should warn you that I've also seen other mathematicians build this a little bit differently. So in set builder notation, you could also just say the things in my set look like n, just the symbol n, and then you could have two conditions if you like. You could say n is a natural number and n is between 5 and 9. So both of these builds are perfectly fine. You might prefer one to the other. I prefer this one. Maybe it's because of the way I was taught or because it just kind of looks nicer to me. Both are perfectly fine. Okay, so for the next one, maybe we could say that we have a set, and our set contains a letter. So maybe X is a letter such that X is a vowel. Okay, so it's as simple as that. Okay, the next one is kind of similar to what we had above. So we're building a set where we have a natural number. So n is a natural number, so boldface n, and such that n is between and including 5 and 66. So remember the ... means everything in between, and we're counting 5, 6, 7, 8, 9, so we can assume that 10, 11, all the way up to 66 is in the set. In the next example, we also go up to 66. It's just this time we start at -4. So just kind of copying from above, we have our number n includes -4, and it goes all the way up to 66. So this time we don't want to say that n is a natural number because it could also be a negative number or 0. So we would say that it's in the boldface Z set of integers. Okay, this next example, we have 5, 6, 7, and then it just goes dot, 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 up, 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 all the way up. So again, we're back in the natural number zone. So we can use boldface n, and this time we can just say that n is bigger than or equal to 5. If you wanted to use a strictly bigger than 4, you could do that as well. I kind of like bigger than or equal to though. In the next example, we have a fraction, and again we have dot, 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 so our pattern continues on and on and on. And it looks like this time we have 1 over 2, 2 over 3, so it's one more on the bottom. So I'm going to write it in that way, where I have a number on the top and then one more on the bottom. And I think it's nice to clarify that this number is in my boldface Q, my set of irrational numbers. We don't necessarily need that because the symbolism already is describing that we're in rational numbers, especially if we define n as an integer, which we're about to do. But I kind of like writing the Q. Okay, so such that n is a natural number and such that my n is bigger than or equal to 1. So n just goes up and up and up, and every time what's ever on the bottom is one more. Okay, so if we wanted to represent all rational numbers between 0 and 1, we could say that this is, maybe I'll use r for a rational number. So my rational number is in Q, and such that my r is between 0 and 1. I think this time I should use strictly less than symbols because it says between 0 and 1. All right, the next one is a little bit tricky, and it comes with a little bit of experience practicing with some different sets that are out there. Now, staring this one down after a little bit, I recognize that it's similar to a set that I know about with the squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 times 5, 5 squared is 25, and so on and so on and so on. So it's really similar to that set. So what I want to do is add 1 to each of my squares. So I'm going to write that as n squared plus 1, such that n is natural and n is bigger than or equal to 1. Now keep in mind that the way I'm writing these sets is not the only way to write the set. I gave another example right here of some other choices that you have. As long as what you're writing down is describing every single number in the set exactly, it is a correct way to write it down. If I had instead written z here, it would be okay because you're still having the condition that it's still between 5 and 66. But I think it's just a little nicer to restrict it more so you already know that you're talking about positive integers as soon as you read that first part. So there's a matter of taste, at least a little bit, when you're writing down these sets. Okay, one more example. All right, so in this example, I'm noticing that all the numbers are really close to 2. So maybe I'll write down a little sample here. The first one is like 2 plus 1. And then the next number, 2.1, is 2 plus a tenth. And then the one after I have 2 plus 100th. And then it's 1,000th and then 10,000ths. So all the numbers are close to 2, just a little bit more. So let's see if we can write this in builder notation. So we have 2. What do the things in the set look like? They look like 2 plus something. Okay, what is my something? It's going to have to be a power of 1/10. So depending on which stage along this pattern we're at, will tell us how far we go. So we need to describe this with my conditions. So my n will be a natural number again, or actually maybe I need to be a little bit careful. I might also need 0 to represent this first one. So it's not just a natural number, I think I'm going to need 0 as well. So I'll write an integer and another condition such that it's an integer bigger than or equal to 0. So now when I plug in all of these values, plugging in 0 right here gives me 2 plus 1, so that works. And then plugging in 1 here gives me 2 plus 1/10. And then plugging in 2 right here gives me 2 plus 100th, and so on and so on and so on. So this is one way that you can put this set from list notation to builder notation. All right, so there's one last thing I'd like to discuss with you. It's optional if you want to stop here. It's returning us back to the warm-up problem. Remember, there was a warm-up problem that's talked about the set of all sets that do not contain themselves. I'll discuss that now. So how could we notate this? Now, sometimes mathematicians have discussed putting sets inside of sets. So it might seem a little bit funny, like maybe you have the set of all pets. So we have P for pets. And then inside of the set, we have maybe a golden retriever. And maybe we have a lab. And then maybe you get tired of listing the dogs. And then inside of your set of pets, you put another set of all dogs. Okay, so this is allowed. There's nothing wrong with collecting sets. We said that inside of our sets, the elements can be anything that you like at all. So why not a set itself? Now, Bertrand Russell was thinking about this problem and other mathematicians in the early 1900s, and they wanted to have something solid to discuss as we now know it as set theory today. And one of the contemplations about making it solid was, well, what can go inside of sets? What's my limitation? And maybe a limitation here is it would look a little bit funny if we put P as a set inside of this set. I think that kind of forms a bit of a contradiction, because what is P if you put P inside of P? So Russell said, okay, we're not going to do that. We're going to collect all the sets that don't contain themselves. But it turned out that that also formed a contradiction. So let me explain. Okay, so let's try to write down this goofy set. So the set of all sets that do not contain themselves. Let's try to put this in notation to help us understand. So we'll use builder notation. We'll say A for the set of all sets will equal S is a set such that S does not contain itself. So we're not going to put S inside of S. Now the question is, well, what about this set A that we've built? Should A be inside of A? So maybe we'll suppose that it shouldn't be inside of A. This is the thing that we're trying to avoid. And now we look at our conditions. Our conditions say that in order to be in this set, we need to be a set itself. So A, yep, is a set. And the condition is that it's not supposed to contain itself. Oh, we meet the condition. So we can erase the is not an element of and replace it with is an element of. Okay, so now we're in the set. And then we say, okay, being in the set means that we're a set. Yeah, we look like we're supposed to be in the set. And the condition that we're supposed to follow is that we're not supposed to contain ourselves. Oh, well, this is now not true because I'm in the set. So I don't contain myself. So you can go back and forth with this particular contradiction and notice that it doesn't make any sense. So it's just a fun example to show that there are some limitations to anything at all can go in a set. Now, I don't think that we need to really think too much about this, especially for this particular course. There's other examples out there in the English language that create contradictions with rules, and sometimes you just need to avoid certain scenarios. So, like some rules in English we might have to avoid, like the painter that paints all those that do not paint themselves. Is this painter willing to paint themselves? Well, you could say that, so this painter wakes up one morning and says, "Will I paint myself? No, I'm not that vain. I would never paint myself." And then the painter looks at the rule book and says, "Oh yeah, I won't paint myself. That means I can go ahead and paint myself." So sits in front of the mirror and paints themselves. And now he's just broken the rule of willing to paint themselves. So the rule itself forms a contradiction, so it's not a rule that can be universally followed. Another quick example, I am a person that always lies. So if that were true, maybe you'd go along the rest of your life and lie every time, but then this statement itself would be true. So again, you can't universally always follow this, and mathematicians have kind of struggled with these ideas. Just a fun little anecdote to this introductory into sets. Okay, thanks for listening all the way to the end, and I'll see you next time.